to part 4 in our Gödel's Incompleteness Theorem videos. I'd like to congratulate you on getting this far. I think parts 1 through 3 are both the most difficult and probably the most boring as well. So if you made it to this point, I think parts 4 and 5 will be far more rewarding and potentially a little less difficult. I'd also like to acknowledge that I haven't actually explained what Gödel's Incompleteness Theorem states or what it is. And I'm sorry about that, but I'm not going to get there until a bit later. So last time we developed our wonderful typographical number theory, which we call TNT. And this time we're going to be talking about the sorts of things you can do with it. Almost every single thing that we will want to do is going to be a property of numbers, and we're going to mostly use this sort of notation. So if I say prime with a there, that means that this is going to represent a string of TNT. A is going to be a free variable in that string. And what this statement of TNT is going to be trying to express is that the free variable A has the property of whatever word we're using. In this case, it's prime. And you'll remember from last time that this is a fairly simple string of TNT. There's really no reason to use this one since the actual string isn't that hard to write, but a lot of the things we'll be discussing are much longer, and in many cases just too tedious to even figure out exactly what the string is going to be. So as long as we know that there is a string, we won't waste our time figuring out exactly what it is, and we'll just use this notation instead. This one is saying that when you substitute the number, which is 5 here, for the free variable a, what you get is this string, and the statement more simply is just going to read 5 is a prime number. And it's important to remember that we don't need to express true statements. 5 is a prime number does happen to be a true statement, but you can also say that 6 is a prime number even though that is not true. Of course, it should turn out that this is not a theorem while this is. And while we're at this point, it's probably worth taking a note of some of the history of stuff that was going on around the beginning of the 20th century. Mathematicians had figured out similar systems to this TNT that we've worked out, though of course they started with very, very basic notions as axioms, and their rules of inference are even more basic than the ones we've been working with here. But it turned out that systems that can do the same amount of stuff that TNT can do are pretty powerful. When it comes to expressing statements of number theory, there's really nothing it can't do. Sometimes it might not be obvious that it can do something. And it turns out that a very, very large number of properties are in fact represented. And when I say represented, what I mean is all true statements turn out to be theorems, and all false statements don't turn out to be theorems. We'll talk about that a little more later, but for now it's just good to get the concept out of the way. A famous example of a number theoretical problem that we would want to be solving would be the Goldbach conjecture. It states that all even numbers greater than 4 can be expressed as the sum of 2 primes. Now it turns out it's pretty easy to figure out whether any given number satisfies this sort of thing, but it's a whole lot harder to figure out whether that's true for all instances. And here we're just going to do the simple thing. We're going to say that a is a number that has the Goldbach property, which means it's an even number, it's greater than 4, and is expressed as the sum of 2 primes. And we've got a pretty long string of TNT here that represents that property. You may or may not be familiar with the idea of twin primes, which is that two numbers are separated only by 2 and they're both prime numbers. And so here we're using an example of something that has 2 free variables. And then if we want, we can even add some stuff to the beginning of the string of TNT. So what we're taking from this into this, so we're going to add this to the beginning, and then we're going to substitute 5 for A. And of course the result is this formula. And what this is sort of saying is that there exists a number B that is the larger number in a set of twin primes, including 5 as the smaller number. We happen to know that this is true, in fact. If you substitute the number 7 in for b, it's going to satisfy this. Now moving on to strings of TNT that we're not actually going to explicitly state out because they're very long and they're rather difficult to comprehend. And if you don't know, the Fibonacci sequence is just the sequence starting with 1 and 2, or 1 and 1, the same result happens. And what you do to find the next number is just add the previous 2, then you get that. 2 and 3 make 5. So what we need in order to figure this out is starring numbers. Here we're using 2, but there are different properties that involve 1, 3, however many. And then you need what to do to the starring numbers in order to get the next number. And now we're going to be talking about some more complicated property. We'll start with the number 31 just because, but then we have a few different options that we can do. Those of you who remember part 1 pretty well are probably thinking that this looks pretty familiar, and you're absolutely right. The very first formal system we looked at, the MIU system, we'll remember these rules as the arithmetic version of the typographical rules we started out with. And we'll represent whatever this very, very long string of TNT that I'm not gonna even begin to try to figure out. We're gonna call it MIU of A. The statement's gonna say that A is a number with the MIU property, or because we know that if we use these rules, they're going to correspond precisely with the typographical rules that we have for the same system. As in, there's going to be nothing we can do with the typographical rules that we can't also do with the arithmetic rules. And conversely, there's going to be nothing we can do with the arithmetic rules that we couldn't do with the typographical rules. So if we substitute all the 3's for m's, all of the 1's for i's, and all of the 0's for u's, we're going to get A translated that way is a theorem of the MIU system. So that's a pretty interesting result, isn't it? Talking about nothing but properties of numbers, we can mimic typographical rules by substituting the arithmetic rules, and find some very long string of TNT that does the exact same thing that our typographical system was doing earlier. And you might remember in the first video that our question was, is MU a theorem of the MIU system? So an alternate but identical way to ask that question is 30 a number with this MIU property? That is, can we start with 31, do nothing but those 4 rules to those numbers, and get the number 30? Or can we take this very long string of TNT that has at least one free variable a here, and we substitute this, which is 30 s's with the 0 at the end and stands for the numeral 30. If we substitute this for every time a appears in this string, is the result a theorem? If this turns out to be a theorem, and we're assuming correctly that every single true statement turns out to be a theorem, and every single not true statement turns out not to be a theorem. This is a theorem. That means it is a true statement, which means 30 is a number of the MIU property, and MU is a theorem of the MIU system. Now wouldn't that just be an awesome use of TNT? Now some of you might have made the logical jump that, since the MIU system is nothing but typographical rules, and TNT itself is nothing but typographical rules, what's stopping us from doing the same thing with TNT? And the answer is, of course, that there's nothing stopping us, so let's do it. Gonna take all the symbols we've used in TNT, but we're gonna substitute these symbols for these numbers, and we're going to add a symbol for the line breaks. Now, when we substitute all our original easy-to-read symbols out for these kind of harder-to-read numbers, this is what our axioms read. And as much work as it was to write down all of these axioms, the arithmetic form of what we're allowed to do to these numbers to get other valid TNT numbers that correspond exactly one-to-one with the rules that we had is going to be very, very long and very tedious and fairly uninteresting. Certainly though, if all we're doing is shifting around symbols, shifting over 3 digits, which is just powers of 10, or powers of 100, or whatever you like, adding and subtracting from any of those powers of 100, making numbers smaller or bigger, you get the idea. There's going to be some very complex arrangement of doing nothing but those things. It's going to be doing the exact same thing to these numbers that our very carefully constructed rules were doing to the symbols last time. In whatever very, very long string of TNT that represents taking these starting numbers and applying however many very long rules to them and getting a result as a number we're going to call a number with TNT property or a TNT number. What we're really talking about is how it doesn't matter which symbol we choose for all of these notions. We could have mixed these up and it would have been confusing, say, if we had this sign mean addition, if we had this sign mean 0 and this sign mean the successor of whatever number. So just one very arbitrary seeming choice for symbols is 3 numbers. You don't even have to think of them as numbers, you can just think of them as symbols that happen to look like this. What happens when you use symbols that just, happen to look exactly like numbers is that you can treat them as numbers. And as long as the only thing you're allowed to do with the symbols, whether they look like this or like this, if the only things you're allowed to do is shift around the symbols in very specific and perhaps arbitrary ways, then there's also going to be a way to multiply and add the numbers that will mimic the shifting around exactly. So asking whether A is a TNT number, we know that what we really mean is that the number A is a theorem of our TNT that we developed last time. We can see that if we interpret these 3 numbers as symbols, what we're really saying is 0 equals 0. And if you want to figure out the proof of 0 equals 0 within TNT, you're perfectly welcome to. It's not very difficult. And that means that this number is indeed going to be a TNT number. Okay, while all of that was certainly fairly fun and interesting and mind-bending, we're going to have to sort of limit ourselves. When I was talking about the history, I said that a whole bunch of mathematicians spent a long time trying to figure out whether things were expressible or represented. And we decided that primitive recursive properties were certainly going to be represented. And of course you're wondering what primitive recursive is. One way to think about it is whether or not a given search of whatever form for a property, can you tell for sure whether that search is going to end or not? If we substitute a number in for A, are we going to be able to tell whether that number is prime or not in some sort of finite, if unimaginably large, quantity of time? And yes, of course, a prime number is just a number that does not divide into any other number evenly besides 1 in itself. You just start at 2, try dividing the number by 2, that doesn't work, try 3, try 4, try 5, and since we know that once we get to the number A, if we haven't found any numbers that divide it evenly without anything left over, then it's prime. So we can just stop our search at A, or we can stop our search once we find a number that does divide it evenly. But then we have these two, which we were just working with and doing some rather interesting things with. Luckily, we don't have to think too hard about this. We can do everything we'll need to do for the purposes of these videos, only using things that we can certainly say are primitive recursive. Because we can't tell for sure that they are, we're just gonna throw them out the window. We're gonna forget that these two even existed. So we still definitely want to talk about whether or not things are theorems, and luckily, we've got the idea of being a proof pair. An example of what is a proof pair, when we substitute A for this number, and this number for B, go between 3 and the next 3. You separate the lines, figure out if this number to this number is using one of the arithmetic rules, then see if this number to this number is using one of the arithmetic rules, and see if this number to this number is one of the arithmetic rules. If all of those individual steps check out, then the only thing left is to make sure that this number is B, and you have a proof pair. So what this is saying is that we have the entire proof here, and the result here. If 301 is a proof pair of this, then we know for certain that MUI is going to be a theorem. You can always stop exactly once you've got to that last line. So we've got a nice primitive recursive way of talking about whether things are theorems or not. You just need to know the entire proof in order to do it. Naturally, TNT proof pairs are going to be much more complicated. You can think of a proof pair formula as saying whatever B is a theorem of TNT with this proof, and then you actually have to list out the entire proof. If we want to be a little more vague, we can say that if you substitute this number in for B, then there is some A, we don't know what it is, but that forms a proof pair with it. That's the same as the claim that B here is going to be a theorem. In this case, all I'm saying is 0 equals 0 right here, which, like I said before, you're fully welcome to work out that proof for yourself. And I'm not sure if there's anybody out here who caught this. We've been using things A and B, even though if you look at the characters we have substitutions for, I never put a B or a C. And in fact, you can have infinitely many variables just by using A, then A prime, and A double prime, and so on. Obviously, A, B, C, D, and E are easier to read, but I think you've gotten comfortable enough by this point. One thing we've done a lot is take free variables and replace it with a numeral. So I suppose if we had a property that we wrote as equals 3, it would be A equals 3. And then when we substitute a number in for A, we replace it for the number 4, which would give us 4 equals 3, which is obviously not true, but that's okay. We've done so much stuff with proof pairs and theorems and truth and all of that I'd like to take a break for a little while, and substitution has nothing to do with whether things are true or not. Or if we had this formula to start out with, every time A occurs, we'll replace it with 4, which gives us 5 equals 4 plus 2. Now the substitution, our A, is going to be this, which you can probably see with maybe a little bit of effort, but not too much effort, is the same as this. A prime is going to be 4, though of course we'll have to write it like this. So we have the formula to start out with, what to replace it with, and I bet you can guess by now that A prime is going to be the resulting formula. And to wrap this episode up, let's do something a little bit fun with this substitution thing. For A, we're going to use this number. We can see that this is just a Gödel number for the formula that says A equals 3. And what should we do for A prime? What should we substitute in for this A? Well, let's substitute its own Gödel number in there, just for fun. Of course, this is a whole lot of 1, 2, 3s. And then, of course, A double prime is going to be... This is all going to be the same, but what we're substituting out is the 262, which means A. Instead of 262, we're going to do 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on, all the way until after that, many times of that, we've got the 0. And probably the most fun interpretation of A double prime is A equals 3 itself equals 3. Because what are we saying with this huge number? Well, we're saying A equals 3. And what are we putting it into? Well, A, whatever A is, in this case what we're saying is it equals A equals 3. That equals 3. If that seems a little silly or kind of contrived or not exactly mathematically rigorous, we'll talk about that more in the next video, but for now I just thought it would be a fun way to think of things. We'll see you next time.